All right, let's get started. Do you have any questions regarding Lab 1? Any issues? Today's opportunity for you guys to ask me any questions on that. See, Lab 2 extension of Lab 1, okay? It's the layout part of it. You can see, so in Lab 1, we did the schematics, but it's both ideal. ADC and DAC both are ideal circuits. If you look at Lab 2, we're trying to teach you guys two major parts. First, which is a modular design. You can see this resistor string has so many components. In the future, any of these VLSI design experiments or projects, all of these are doing modular design. You can see this one, we can put these three resistors into one module and save it as a cell. In the future, when you are assemble another schematic of this R2R ladder, even though it's a really simple example, it's not any sophisticated VLSI circuits, but it's still reducing a little bit of the hassle and workload a little bit. So what you do is you have grab this one and build a module of it, out of it. So the way to do that is this. So this part becomes a little chip. You know, even though it's not really a chip, but it's a module you can use from the library. You can drag and drop in your design, and eventually it becomes a little symbol like this. It's actually called icon in electrical VLSI. Okay, so in that case, the three resistors, which is part of the R2R ladder, you have to have ports. We found issues of the students from last week. They are not seeing the ports because they didn't export it. So you need to Control E. And eventually the label of the port looks like this, okay? If you have the name directly on the pin or over here, which means you didn't Control E it. Make sure you Control E to export it. So after that, you create an icon from it, and you will be able to see this, and it has all the ports with it. Okay, so that's a cell. Okay, it's a cell. And on the left-hand side, you can see a bunch of library cells, and this will be one of the cells you can directly use. If you click that little cross sign, you can see the schematic view, the icon view, and the layout view you are going to build in a bit. So now we have schematic view, icon view, right? So to create a complete cell, we need a layout view as well. So let's skip this one for now. So here's a layout view. I think it's from create and create the layout view. Or you can right click this cell and create the layout. Okay. So based on the sheet resistance that we covered yesterday, I can do a calculation for the length and width. So length divided by width, you are getting how many squares are in there, and times that sheet resistance, and I think we are getting 10K. But you are going to do the calculation by yourself. I think we have the sheet resistance provided. So it's basically 800 ohms for the sheet resistance for this C5 technology. Okay, and then you put a 10K here. So that's the unwell, the layout view of the unwell. So this area, okay, that's the unwell. It's a top view. So what that is, we think. So unwell is inside the wafer, right? It's the wafer. But eventually, when you are trying to build connections to the unwell, you need a vias. So the unwell itself, at the two terminals, you have a via, and that via connects to the upper layer. And what that layer is, remember from yesterday? It should be metal 1, right? So you got a metal 1 over here, but it's still deep inside the chip. Eventually, you have all these layers from bottom up, and eventually you have metal 3 on the top. And metal 3, on the top of metal 3, there's another silicon dioxide layer, which is the passivation layer. The thing is, there's a certain library component in electrical VLSI that allows you to have a little opening on the top of metal 3. So you can open up the chip, and you can see metal 3 physically when you receive the die, you can really see it, right? And then you use a wire bonder to bond the metal wire to that metal thread. That's how that works. Eventually, you can really communicate with the outside world by doing that, okay? So metal thread is actually the metal that communicates the outside world. So now we have metal 1, okay? And in order to connect to metal 3, eventually to the, just in case you are just making a little resistor on the chip, right? Eventually you want to probe it on the chip, see the resistance using a multimeter. So you do need a metal 1, and then directly on the top of metal 1's, on the metal 1, you need a via to metal 2, and then via to metal 3. So it's like resistors over here. You have metal 1, via, right? And eventually metal 3. Then you can probe it. That's how that works. Okay. But now it's still inside the chip. We are not just directly using the resistor for the final design. It's just a chip. In the final design, if you are using this DAC, you are going to have metal 3 eventually, but now it's just a subcell, still a subcell, even for the DAC, it's still a subcell in the library. Okay? So we don't really need a metal 2 and metal 3, just metal 1, which is fine. You just leave the ports available in the future. When we use the DAC for bigger design, we can connect all the vias to metal 2 and metal 3 in the future. But I can see this little area is the metal 1's unwell to metal 1's via, which is a little square in the middle. That's a via. And this light blue color is metal 1. Just keep that in mind. So this is one 10K resistor. To save space, I put another one just below it. It has 3 in 3 rows and use the connectors. So that's one terminal, and this here, and connect here to the left, and then that's the output on the right hand side. So this one has a similar structure as the schematic over here. Okay, and you can see the ports. A lot of things are very necessary. First, the 10K resistors, they have to have the same value. So the schematic has 10K, and your layout has to have a 10K as well. And you can see the for this subcell. So one more question: why do we need a port over here? Why is that? Take a look at the ladder. So if you take this part as a subcell, right? We need an input on the left, so we need a 1 port. And we need a 1 port over here as a final output. And we need a terminal below here to connect it to the one next to it, right? So we need 3 ports. But does this one need this port as well? Yes, because it has to communicate with the one above it, right? So that's why every single cell needs 3 ports. Does that make sense? Mm-hmm. Over here we need 3 ports. 3 ports. And have to do the same thing for the layout. So here we want to introduce a concept which is called LVS, but in electro VLSI it's called NCC. Don't worry about NCC, since I don't even know what that stands for. It's okay, because we only care about LVS. It's an industry standard term. It's called layout versus schematic. Keep in mind, you need to know LVS, okay? Because a lot of times in the interview they ask you, did your design pass LVS eventually? Did your design pass DRC? So DRC means design rule check. Design rule check. LVS means layout versus schematic. So they are checking if layout matches all the design and schematic, which is very important. So why do you design schematic? If the schematic makes sense, you have all the symbols, the gates, and you design the circuit using schematics, okay? And then you assign certain ports at different locations, but that's just schematic. But eventually you are not designing the foundries are not looking at the schematic to make the chip for you. So eventually they are looking at the layout. They are looking at the layout. The layout is the physical chip layout. Schematic is just something for the designer to design the circuits using schematics. Okay, so you know that the schematic makes more sense to you, and the layout is for the foundry. But the thing is, before you send it to the foundry, you need to do a LBS because you know that the layout matches your schematic. The schematic your design. The schematic is your design. If the layout matches your design, you know the layout is going to work. So send it to the foundry for fabrication. Make sense? So not just the components or the value of the components in the layout has to match with the design the schematic, but also the ports. Okay, the ports, and there are a lot of other things you need to consider. But now for this very simple design, you can see we have 10K resistors, no problem. And the resistor you picked up in your schematic has to be N-well resistors, cannot be a polysilicon resistor. Otherwise, you won't be able to pass NCC or LVS. NCC is being called NCC in electric VLSI, okay? But it's generally just LVS. It won't pass LVS if you pick up a different resistor in schematic. It has to be an N-well resistor. And for the ports, okay, similar to the schematic, for the ports over here, you left click this little component, which is already available for the N-well, and you left click and right click so you can extend it. You can extend a little metal one piece over here, and you left click the little terminal, the end of this metal piece, and you Control E it. You Control E. So you can export that little metal piece as a port. So that port will match the exported port in the schematic on the left hand side. Same for this one. So this one, even though you are not necessary to extend it as a metal and then you export the metal, you can also export this little node that came with the N-well resistor. So the N-well resistor component, you see here on the top, here. See, I haven't done anything with it. That's the original part component from the library. It already has this N-well and also already gave you that little terminal with a metal one piece on it with the via. So it comes with it. So what I'm trying to say is over here, two ways to export that terminal. First, you left click and right click it to extend it and then export the little metal piece over here. Or you can directly click export the connector on the N-well resistor, which exists already, which comes with it. It's gonna work. So just left click this terminal and Control E. So you have 1, 2, 3 ports, which matches the schematic ports. It's gonna work. It's a modular design. And you also need a layout icon. You need a layout icon for, wait, is that layout icon? It is not. So there's a little button you can click and you can make the details of the circuits invisible. But I think this can be confusing, all right? This can be confusing. What's really happening over here? So you create a schematic, you draw a schematic, then you create an icon from it, and you don't touch it. And then you create the layout view. You create the layout view, which is the layout view over here. And why it looks like this. So keep in mind, a subcell is a subcell. It's another library component. If you look at your R2R ladder is over here, I name it V2, doesn't matter, it's just an R2R ladder. That's a different cell. So the subcell is the one has 3 resistors, has an icon, and has a layout over here. Okay? And why it looks like this? Because when you want to use it for your overall R2R ladder, because the subcell only had 3 resistors, but for the entire deck design of the layout, you need the subcells, right? The multiple 3 resistor subcells. So how to use it? Never insert it or never click any of the buttons on the menu. The way to do that is just simply drag and drop. Keep in mind, this is very confusing. Students make mistakes in the past semesters. For example, subcells layout is done, right? Sitting in the library, it's done. On the left-hand side, it's done. And when you are creating your new schematic for the entire DAC with all the 3 resistor subcells, right? You create another cell called a deck, the R2R deck, whatever that is. It's a new schematic. And you need to create a new icon and new layout. Okay, that's the entire circuit. And within that new layout, you want to reuse that 3 resistor subcells layout. So how do we reuse it? Just drag and drop. Left click, drag and drop. So if you drag and drop, you're going to see something like this. A big box. Okay? I think this is a layout of the entire circuit, the ultraladder entire circuit. And here's the schematic, the layout view I created. And now I start putting multiple of these ones in here. How? I drag, drop for multiple times to create the whole ladder. I hope you are getting that kind of idea of modular design of VLSI design. It happens a lot in the future. You can imagine for a big CPU circuit, there are gates, there are modules, there are different flops. It's going to be like multiple layers of design. See? You drag and drop multiple ones in here and stack them onto each other. But leave a certain distance. Okay, I think this is another way to do that, which is just directly create an array. You can see if you drag and drop one, and then you can create the array just by clicking edit array and put 10 cells in there. And that's going to align all the cells for you and also create a good distance between each other by complying with the design rules. It's not violating the design rules. So, like I said, you could drag and drop multiple ones by yourself, but the better way to do that is just creating an array by doing that, by following the instruction over here. And you can see the circuit. If you look at the circuit, you can tell that eventually you need a little 10K resistor at the bottom because the subcells, the little tail resistor is just 10K, but you need a 20K over there. So after you placed all the subcells, you just have to manually add another unwell resistor at the bottom to make the circuit complete. So it's matching the schematic. Another requirement, because I think everyone's over here right now, we're not missing anyone, right? I don't know. So in your report, you have to make a snapshot of the DRC check, error freight message window, and also NCC check message. So it's basically, you see here, running DRC, 0 errors, 0 warnings. Warnings are not also acceptable. I think we shouldn't have warnings as well. And for NCC check or LVS check, I need to see exports match, topologies match. I have multiple lines, I think we just did it multiple times. But this is what you are looking at, okay? Exports match, topologies match. I will deduct the points if you don't have this message displayed in your report. Okay. And eventually, how do we want to simulate it? Here's the general idea about this one in the circuit design industry. So for layout, for this pretty simple software, open source simple software, we already learned how to simulate schematics last time, right? But how do we simulate layouts? In Cadence, there's a different way to do that, but just for electric, can we connect an icon of the layout to the schematic of the ideal ADC? Because this is the final result we are expecting, right? We see this, we claim a success. But now, this is ideal ADC. There's no way to lay out ideal ADC. It's not a physical device. So this one is a 10-bit ideal ADC. It's just a schematic. Okay, there's no layout with it. But we are doing the layout today for the deck. How can we connect one to the other and make a simulation? The answer is we can't. You cannot connect the layout to a schematic and run simulations. You can still run simulations with just the pure layouts, which is fine. It's going to work. But there's no way that I can connect the layout to a schematic, even especially this is a ideal schematic. So there's no way to do that. So what we put in here is a new schematic you just created from this lab, which is a modular design instead of the one from last week. Keep in mind, you have all this modular design, and then you wrap that up to create another upper layer schematic. It's basically the same thing, but this one has a modular design, has 3 different layers, but the one we did last time was just manually laid out resistors. And you can imagine last time, since you manually drew the all the resistors over there last week when you are doing the schematic. So what's gonna happen, right? What's gonna happen last time was you grab this one and then you place another resistor, you place another resistor, you make the connections, all right? And then you start placing more resistors. You use your mouse to place more resistors. Sometimes you took too much coffee in the morning, your hands are shaking, and so you place a resistor here, a resistor here, resistor here, okay? And one here, one here, one here. So depending on different hands, you'll see all different types of schematic view in your report. I will see different types of schematic. And then you start making connections. Okay? Does this look good? Yeah. It's not right. It's not a right way to do things. And then you find issues, you do the DRC check, you have a bunch of issues, right? So sometimes you make a good connection here, sometimes the connection here is not a good connection, not a good joint, and you'll see DRC issues. You see DRC issues, you have we have maybe 30, 20, 30 or something, those resistors, still fine. What if you have 1 million resistors, 1 million components, and you do DRC, boom, you got thousands of DRC errors. Then you have to go back to the original design and manually fix every single thing. And that's the benefit of doing modular design. Can keep it clean. So what you are going to do is, like for this one, right, we create a 3 resistor module. And we put this module in the box. And we do DRC check with this sub-module, even LBS as well. We create a sub-module, we create a layout version of the sub-module. Okay? It's done in the library. And then we do a LBS, we do DRC, both are clean, okay? We know this guy is safe to use. Then we start building a bigger one above it, so we directly put a box over here. So we get rid of all the issues of alignment and inconsistency inside the box. But we still have issues over here when we're placing boxes over here, but which is fine. We can create an array, use the software to create an array, so we can directly create an array of these letters, all right? And then we wrap these up in another box, okay? So we know this passes DRC, passes the LBS, is clean, it's all aligned with each other. So we put this one as one box, we call it DAC. In the future design, a chip design, we need 100 DACs. So we just directly use 100 of these boxes instead of drawing every single resistor by ourselves, manually for each one. So if you do DRC and LBS, for example, for this stack, okay? DRC, LBS, we see issues. And we know the issues will be just the connections between the boxes inside the boxes. Because inside the box is already done. The LBS and DRC done. So we know it works. So if you see issues over here, there will be only like 10 problems or errors instead of 100. Make sense? So this one is a modular schematic. It's not a layout. So put a modular schematic and connect it with the ADC and do the simulation. If it works, it's a success of the lab. And I think this one is relatively simple. We don't have too many things covered in here, but just letting you guys know a modular design and run DRC and LBS checks and a sheet resistance calculation, and that's it. Any questions on this? Okay, I get started.